We're going to have an hour exam in class coming Monday, a week from today. It will cover all the material, well, really from the first hour exam, but you'd have to know the definition of a group and things like that. So all the material that we've covered through today's class and including today's class. That's what through means. It's less than or equal to today's lecture. And that Peter will do a review of this material in class on Friday if you want to go over this. I'll be in New York City. Then next week, for those of you who are making Thanksgiving plans, we'll have the hour exam on Monday. Wednesday, I will go over the exam and give somewhat of a special lecture so that if you've had to take off by then, you won't be penalized. However, you'll miss an incredible amount of good stuff. Okay, so last time we were at the canonical map. If we have an R, a commutative ring, there's a natural map from the integers to the ring, a ring homomorphism, which is completely characterized by the fact that f of 1 is 1 in the ring. That would have to be the case if it were a ring homomorphism. And then it's additive, so f of n, which is the integer n, which is where n is bigger than or equal to 1, would be f of 1 plus 1 plus 1 n times, which would have to be 1r plus 1r n times. And then, of course, f of minus n, if n is positive, would have to be minus f of n, which we know already what it is, and that determines it. So that tells you what it is on every integer, and then you have to check that that's multiplicative, and it is. And it is, by the distributive law. If you multiply 1 plus 1 plus 1 plus 1r n times by 1 plus 1 plus 1 plus 1r m times, you get the same thing mn times by the distributive law. So this is a ring homomorphism. It's the canonical ring homomorphism associated to any commutative ring. Now we know that the kernel is an ideal of Z. So we know it has the form n times Z for some n bigger than or equal to 0. Because those are all the ideals of the integers. For example, if R is the 0 ring, the kernel is everything. Because 1r is 0. So f of 1 is 0, so f of everything is 0. So the kernel can be the 0 ideal. Then the ideal, so if, let me write this down. If R is the 0 ring, ker f is equal to Z. If R is equal to a ring like Z, or Q, or the real numbers, or the complex numbers, then all of these numbers are non-zero in the ring. And so then the kernel is just 0 times Z. In that case, it's an injective ring homomorphism. Of course, if R is some finite ring, then the kernel of f is nz. So you can have pretty much anything for a kernel, depending on what your ring is. Okay, however, I'm going to prove the following proposition. If R is a field, the kernel of f is either the 0 or pz for p a prime. You can't have an arbitrary kernel if you have a field. And the proof is like this. Suppose the kernel of f is equal to nz, where n is composite. So we're going to make a proof by contradiction. And we write n as a times b, with a bigger than 1 and b bigger than 1. That's what we mean by a composite number. Now, that says then f of n is equal to 0 in R. That's what it means for this to be the kernel. But f of n is f of a times f of b. Okay? So we have numbers here, f of a and f of b, which we could call a sub r times b sub r. And that's what I'd call this number, by the way. This is the number n in the ring R. It might be 0, but it's a well-defined number. So we'd have these two numbers having product 0. Now, in a field, if a product of two numbers is 0, one of the numbers must be 0. Because if A is non-zero, then this is equal to 0R. So we have this expression. If AR is not equal to 0, you can multiply by AR inverse, because in a field, non-zero elements are invertible, to get BR is equal to 0. So 1 of AR, BR must be 0. But that contradicts the fact that the kernel is multiples of n. Because when you have a factorization of n like this, neither a nor b is a multiple of n. This is a contradiction. As AR and BR are not elements in NZ. So notice that this goes wrong for rings like this. If you take Z mod 4Z and you multiply 2R times 2R, you get 4R, which is 0 in the ring, but neither of these elements are 0 in the ring. But for a field, you can't have that happening because of inverses. And so for a field, the only possibilities is 0 and PZ. And we've seen that we can have 0. For example, this is a field where the kernel is 0. And we can have PZ. For example, Z mod PZ is a field where the kernel is PZ. So this is an invariant of any field. What the kernel is of this homomorphism, and it's called the characteristic of the field. In this case, we say the field has characteristic 0. And in this case, we say the field has characteristic P. Characteristic. It's just a piece of terminology of the field. Field is equal to 0 or P. And it also lets us prove a nice theorem of Galois. Well, we'll prove the first part of the theorem of Galois, which I think I told you before, which is theorem. Galois invented the theory of finite fields. Let F be a finite field. Then the number of elements in F is a power of P. You can't have a field with 6 elements in it. You can't have a field with 15 elements in it. Okay? Even though you can have groups or rings, notice that you can have finite rings with any number of elements in it. There's a finite ring with n elements. But for fields, it has to be a power of P. And the proof is, consider the canonical map, homomorphism, Z goes to F, n goes to n sub F. All right, this is an infinite ring. This is a finite ring by hypothesis. Therefore, there has to be a non-trivial kernel. Since Z is infinite, kernel of F, because the image of Z the image of Z is a subring of F, so the kernel of Z also has to be infinite. Kernel of F is not equal to 0. Otherwise, that would give a copy of Z sitting inside of F, which would give F an infinite number of elements. Right? So the kernel of F is non-zero. And we've seen for a field, that forces the kernel of F to be a Z mod P. So kernel of F equals PZ. And F induces a homomorphism, F bar maybe, from Z mod its kernel into the field F. Now this is an injection because we've modded out by the kernel in the usual way we did in group theory. Now this you can multiply things, but at the very least you can multiply them by elements in this subring. So this gives F the structure of a vector space over the field Z mod PZ, forgetting about the fact that you can multiply two elements in F, just using the fact that you can add two elements in F and you can multiply them by elements here. That's the structure of a vector space, where these become the scalars. I mean, of course, F is a one-dimensional vector space over itself. But here we now see it's a vector space over this field, which has finite dimension, as there's certainly a finite spanning set if there are only finitely many elements in the field. Just take all the elements, they span F. So if F is, say the dimension is equal to F, then the number of elements is P to the F. Just choose a basis and write elements in terms of coordinates from Z mod PZ. So as a vector space, F is isomorphic to Z mod PZ to the F as a finite dimensional vector space. Of course, that doesn't tell you what the multiplication law is on F, but at least it tells you what the size of it is. That's Galois proof. Now the hard part of this theorem, which I can't prove for you now, but I promise you will be proved in Math 123, is that Galois also proved that for any F, there is a finite field with P to the F elements. We don't know that yet. Namely, it is possible to put a multiplication law on that vector space. So we don't even know yet that there's a field with 4 elements. 4 elements. We know 2, we know 3, we know 5, we know 7, we know 11. Any prime we can make a field, but we don't know 4, we don't know 9, we don't know 16, 32. But Galois proved the existence of such a field, and he proved not only that, he proved it was unique up to isomorphism. In fact, there is a unique such field of order P to the F up to isomorphism. Namely, if you have two fields of order 4, they actually are isomorphic to each other. So that's a very cool thing that Galois proved, which you'll see, and that's a very important thing in number theory too, which you'll see in Math 123 when you do field theory. The subject of Math 123 is really the subject that was invented by Galois in the last year of his life, which encompasses both the theory of fields and the theory of groups in a very beautiful, interactive way called Galois theory, named after him. And one of the first triumphs of Galois theory was the construction of these finite fields. Okay, let's go on. Now, I talked a little bit about quotient rings, and I want to talk what they call the first isomorphism theorem of rings. It's exactly like it is for groups. So, quotient rings. So here we start with a commutative ring and an ideal. And when we have that situation, we have a natural homomorphism to the quotient ring, which I'll call R bar. And it's a surjective ring homomorphism. So we've seen this from the theory of groups where the ideal is like a normal subgroup. Now, the first isomorphism theorem gives a relationship between the certain ideals in R and certain ideals in R bar. And it says there is a bijection between, on the one hand, ideals J in R that contain I. So we'll put them like this. ideals of R containing I, and they're in bijection with the set of ideals J bar of R bar. So you get all ideals of this quotient ring by taking ideals of R that contain I. I'll give you that bijection. And the bijection goes like this. To a J, we associate the image of J in R bar. And we're going to see that that's an ideal. And to an ideal J bar, in R bar, we associate the pre-image of it in R. And we're going to see that's an ideal that contains I. So there's an important bijection. That's like the bijection between subgroups of G containing a normal subgroup and subgroups of the quotient group. Same kind of bijection. And moreover, the quotient of R by J, this ideal containing I, is isomorphic to the quotient of R bar by J bar. So you get the same quotient rings. So this is like many of these very general theorems, the isomorphism theorems, it's more or less a tautology once you figure out what is actually going on. So let's check a few of these things, and I'll let you check the rest as you go through it. So let's see that this f of j is an ideal of R bar. Well, you have to check that it's closed under addition and multiplication from R bar. So let's assume that, so we have f of a and f of b are elements in f of j, where a and b are in j. Is there some in f of j? Why? Exactly. Then f of a plus f of b is equal to f of a plus b is in f of j, because the sum of these two things is in j. That's what I mean by tautologous. But the next one's a little tricky. Suppose f of a is in f of j, and that we have an arbitrary element, R bar, is in R bar. Is R bar times f of a in j bar. In f of j, I'm sorry. That's the point you have to use. And this is not true for an arbitrary homomorphism. You see, this happens to be a surjective ring homomorphism. Since f is surjective, we can write R bar as some f of R. And having written R bar as some f of R, we write this as f of R times f of a, which is f of R times a, because f is a ring homomorphism. And this is an element in J, because J was assumed to be an ideal. Very good. But if we didn't have a surjective ring homomorphism, then you just can't take f of an ideal and get another ideal. Be careful about that. Okay? For example, f of R might not be an ideal. Let's just show you that. I mean, so this is a warning here. If f is not surjective, f of j need not be an ideal. So you don't have an obvious map if you have. So, for example, if you take the integers and you include them in the rational numbers, that's a ring homomorphism. Not surjective, of course. If a perfectly good ideal of the integers is z. If you take f of z, you get the integers in here. That's not an ideal, because the only ideal of the rational numbers are 0 and q. It's a field. Okay, so you needed the surjectivity to be able to write this r bar as f of r. However, the pullback works in any case. Whenever you start with an ideal here and you pull it back, you get an ideal in r. I'll let you guys prove that. But notice that this certainly contains I, because I is f inverse of 0. That's the definition of I, because this homomorphism has kernel, surjective ring homomorphism with kernel I. And whatever this J bar is, it's an ideal, so it certainly contains 0. And so its inverse image contains the inverse image of 0, so it contains I. I'll let you check that it's an ideal. And to identify these two quotients, you just compose this homomorphism here with the extra quotient map from r bar to r bar mod j bar. So you take the composition of these two maps. This is another quotient. And the question is, what is the kernel of this composition map? Well, the first thing is that the composition map is surjective, because it's a composition of two surjective homomorphisms, both given by quotient rings. So it's surjective with kernel. Well, its kernel are the elements in R such that when you map them to R mod I, they land in J bar. Correct? So that's exactly the things which are in F inverse of J bar. The things which are in R that map to J bar. So F inverse of J bar turns out to be J. I mean, you have to check that this thing, if you go around once, you get back to where you started. So this kernel equal F inverse of J bar, which is equal to J. And so if you have a surjective homomorphism and you know its kernel, it identifies the quotient of this by the kernel with the image. And that's this. That's the proof of that. So this is an incredibly, as I say, it's a tautologous theorem. And you should look through the proof. That doesn't mean you can't know the proof. You have to know the proof. But it has a number of very useful corollaries as you keep it in your mind. For example, we've shown that something is a field if and only if it has only two ideals. So when is R mod I a field? For which ideals is the quotient a field? Well, we have a bijection between the ideals of this quotient ring and the ideals of R containing I. So it's if and only if R bar has only two ideals, 0 and R bar, which is the same thing by this first isomorphism theorem, is saying R has only two ideals containing I. The ones corresponding to those. Well, of course, the one corresponding to R bar, if you pull back R bar, you get everything in R because the thing is surjective. And the one corresponding to 0, if you pull back 0, you get I. I is the kernel, which are R and I. Namely, there's no ideal, if you look at this, if you look at R containing I, there are no non-trivial ways you can squeeze an ideal in here. It's either equal to this or it's equal to that. Okay, so we might say, and we will say, that I is a maximal ideal of R. There are no proper ideals between it and R. If and only if I is a maximal ideal of R. So that's a very good characterization of the ideals that give quotient fields. They're the ones which are maximal ideals. Now, there have to be some maximal ideals. Even in a field, there have to be some maximal ideals. Like 0 is a maximal ideal in a field. And so when you have maximal ideals in a ring, they identify which quotients of them are fields. Another nice thing about this theorem is that you can go to quotients successively. So the book talks about creating relations in a ring. That's an important notion. Suppose we have some element A in R, which could be a combination of generators. For example, if the ring were polynomials in two variables, A might be some combination of x and y. And we wanted to get to a ring where that relation was 0, where that combination of our generators was 0. Well, we could arrange that. If we want a ring R bar, which is an image of R, where A bar is equal to 0, where the image of A is 0, then the largest such quotient is the ring R bar, which is R modulo the ideal generated by A. Because in this ring, A maps to 0, and conversely, if I had any image of R where A was equal to 0, then all multiples of A would have to be equal to 0, because any multiple of 0 is 0. So I would certainly have all of this ideal going to 0. So if the simplest thing I could do is just to mod out by this ideal and nothing larger. Okay? If we want a ring where we have a number of relations, A1 is equal to A2 is equal to A3 is equal to AN is equal to 0, we could take the ring R bar, which is R modulo the ideal generated by A1, A2, up to AN. Again, if you had all these equal to 0 in a quotient ring, then any combination of them, anything of the form R1, A1 plus Rn, An would also have to be equal to 0. And these are precisely the elements in this ideal. But it also says that we could get to this ideal, we could get to this ring by writing this ring as R mod A1 modulo the image of A2 modulo the image of A3. Namely, we could create the relations one at a time in the ring and continue to make successive quotient rings, because let's just think of two relations. The ideal generated by A1 and A2 contains the ideal generated by A1. So that would be like an ideal J, and the ideal A1 containing the relation A1 would be the ideal I, and that would say if you first mod out by I, and then you mod out by the image of J in R mod I, you get the same thing as if you had modded out initially by J. So that in creating relations, you can create them all at once by taking the ideal generated by all of these, or you could first go to the ring where A1 was 0 and then mod out by the relation which was the image of A2, and then take that ring and mod out by the image of the relation A3. You have your choice. In any case, this is a way of creating relations in a ring, and we're going to see next time the relation of adding elements to a ring, and with those two techniques, we're going to be able to build all kinds of new rings out of old ones. All right, well, let me talk a little bit more about specific relations in a specific ring, because you'll see pretty soon we're going to get into some fascinating problems. With all this abstract nonsense, we're going to have a good language to talk about some real problems in number theory. So the rest of this lecture, we're just going to work with the ring of Gaussian integers. So all things of the form A plus BI, where A and B are integers. Okay, now suppose I want to make a new ring where I have the relation that 2 plus I is equal to 0. So this says, well, just take the ideal that just generates, well, multiples of 2 plus I, whatever that is, we don't know yet, and consider R bar is R mod I. And what we'd like to know is what we're left with. Maybe we've modded out by everything. Is this the zero ring? Maybe this is a unit. And so by modding out by the ideal generated by a unit, you mod out by the entire ring. Maybe we have the zero ring. Maybe this is very far from being a unit. We have a gigantic ring left. So we want to identify R bar. Okay. So you do that by playing a little bit around with the arithmetic of this ring. So the first thing I want to notice is the following. So first, let's identify the intersection of I, this ideal, with the integers. Namely, which things lie in this ideal are multiples of 2 plus I, but have second coordinate 0, so they're just of the form A. That'll be our start to identifying this quotient ring. Okay, so I claim that first of all, I claim that 5 is an element in I. First claim. 5 is an element in I intersect Z. So that I can write 5, the integer 5, as a multiple of 2 plus I. Here it is. Okay? If you multiply these out, the I terms cancel. You get 4 plus 1. 5. Okay? So that this thing is not empty. It certainly contains the element 5. Therefore, it contains all multiples of 5. It certainly contains 5 times Z. Because this is an ideal. Right? So if once I have something in it, like 5, I can multiply by anything in the Gaussian integers. So in particular, I can multiply by anything in the integers and stay in it. So once I have 5, I have this ideal. Okay? Now this is a maximal ideal of Z because you can't fit anything between here and here. 5 is a prime number, right? So possibilities are either this is all of the integers or it's just this. That's it. So just from this stupid calculation, we see so I intersect Z, which is certainly an ideal of Z, is either all of Z or 5Z. And we have to decide which it is. Second claim. If I multiply 2 plus I by something of the form A plus BI, and it's an integer, then this integer is divisible by 5. So we're going to prove it's 5Z. We're going to prove that that's the right answer. If this is true, then it is in 5Z. Okay, we have to actually make a calculation to see that. So let's make that calculation. The way we make that calculation is to multiply these two things out. This Gaussian integer is 2a minus b plus 2b plus a times I. Okay? Now to say that it's an integer says that this number is equal to 0. So that means that a is minus 2b. If I put it in there, I get that this number is minus 4b minus b, which is minus 5b. So it's a multiple of 5. Okay? So we know that if the intersection here is contained in multiples of 5, on the other hand, it contains the number 5, so it contains all multiple of 5s, so it's equal to 5z. Okay, so that says that if I make my map from Z to R mod I, the canonical map has kernel 5Z and image Z mod 5Z. So whatever this thing is, it's a vector space over Z mod 5Z. But I claim that the image is equal to Z mod 5Z. In fact, R bar is isomorphic to Z mod 5Z under this map. Namely, it's surjective. Everything mod I is in the image of Z. In other words, yeah. Yeah. And the reason of that is, it's clear. Look, if you look at this I, we see that I is congruent to minus 2 modulo I. So if we go in the quotient ring, I is equal to minus 2 because this element is 0. So since I is equal to an integer, any multiple of I, so bi is congruent to minus 2b, and consequently a plus bi is congruent to a minus 2b in R mod I. Okay? But this is an integer. So the image of everything in the Gaussian integers in R mod I is the same as the image of the integers in R mod I. The image of the integers is Z mod 5. The image of everything is everything, so the whole quotient ring has to be Z mod 5. So after all these calculations, I conclude that this ring is isomorphic to Z mod 5Z. Yeah? Okay, look here. This is the ideal, 2 plus I. It's generated by 2 plus I. When I go to the quotient ring, this element becomes 0 in the quotient ring because it's in the kernel of the map. Therefore, 2 plus I is 0. Therefore, I is equal to, in the quotient ring, minus 2. Therefore, any multiple, integer multiple of I in the quotient ring is minus 2 times that integer. But the arbitrary element in the ring is of the form an integer plus an integer multiple of I. An integer is congruent to itself, and b times I is congruent to minus 2b. So that shows that the image of this in R is the same as the image of this, which is in Z, in this quotient ring. So that everything is in this quotient ring is the image of Z. Namely, this map is surjective. That's not apparent, but it is. And we've shown that its kernel is 5Z, so that gives this isomorphism. That makes sense? Good. Good. If we didn't know, yeah. All right, so now I'm going to show you what Gauss's mind worked like. So Gauss didn't stop here. He did a couple of examples like this, and then he said the following. More generally, if P is a prime, with P congruent to 1 mod 4, so the prime, 5, 13, 17, 29, the prime numbers that leave a remainder of 1 after you divide by 4, there is an ideal I in the Gaussian integers with, call this R, with R mod I isomorphic to Z mod PZ. So here's the case of 5, where we actually knew it. Okay? So this is a little trickier. A little trickier. So here we go. No, we're not going to use Fermat's theorem. We're going to get to Fermat's theorem.
Oh.
We're going to get to Fermat's theorem. We don't know Fermat's theorem yet. Forget about Fermat's theorem.
I mean,
Gauss didn't know how Fermat proved his theorem. He's going to set up a proof of Fermat's theorem. Let's start with this. This is weaker. This is weaker. Just the existence of an ideal. Okay, proof. The first thing I have to find is what the image of... See, if I have this, I have a map from R to R mod I. Now, you'd have to tell me what is f of I. Well, that has to be some element in here which has order 4, multiplicatively. Right? Because I to the 4th is equal to 1, and I squared is equal to minus 1. So whatever this element is, its square has to be minus 1, mod p. If I had such an ideal, I'd have a homomorphism, and I'd take the image of I, and I better find something whose square is minus 1 mod p. So let's start with that. That's why I need, by the way, this condition. If I had an element of order 4, in Z mod PZ, in the multiplicative group of Z mod PZ, then I certainly need the condition P is congruent to 1 mod 4, because this is a group of order P minus 1. So if I have any hope of finding an element of order 4 in it, I have to have 4 dividing the order of the group, which says that P has to be congruent to 1 mod 4. So I have no hope of finding such an ideal where the quotient is Z mod PZ unless P is 1 mod 4. But the theorem says that if P is 1 mod 4, I can find such an ideal. So I have to tell you what f of I is. Now I'm going to do it a tricky way because we haven't got yet the machinery to do it the cool way. Do you guys know Wilson's theorem that P minus 1 factorial is congruent to minus 1 mod P? Have you ever seen Wilson's theorem? That's because when you write down all the elements, 1, 2, up to P minus 1, you can pair elements off with their inverses and cancel everything except for minus 1, which is its own inverse. So after canceling off all the inverses, which occur in pairs, you're left with minus 1, so that's this. That's the proof of Wilson's theorem. Okay, so if that's the case, consider the following element. Can now consider P minus 1 over 2 factorial. I claim that that's your I. That this is an element whose square is this. Why? Well, if you write down that number, 1 times 2 times... It's construction. Construction. We're all safe. We're all perfectly safe. If you take this element, P minus 1 over 2 factorial, and you complete it, to P minus 1 factorial, this product, we agree, is congruent to minus 1. But this element is minus this element. And this element is minus this element. And this element is minus this element. So the terms in this product are all minus the terms in this product. Right? So this product is equal to this product times the number of minus signs. And how many minus signs are there? P minus 1 over 2. But P is 1 mod 4. So P minus 1 over 2 is even. So you get an even number of minus signs. So in other words, this product is equal to this product as an even number of minus signs, which says that the square of this number is minus 1. And there's your element of order 4. It's kind of a bizarre construction, which you wouldn't normally think of as making any sense. But there it is. So this is our candidate for f of I. Let's call this number A mod P. And now I let the ideal I be the ideal generated by P and I minus a. This is some integer which is well-defined mod p, so it doesn't make any difference if you add p to it because I've already got the ideal generated by p. So I is generated ideal by p and I minus a. It's generated by two elements. Okay? I claim that this does the job. This does it. And the way you check it is you check again that I intersect z is pz. It certainly contains the ideal p, so it's either pz or the entire integers. So all you have to do is check that if you have a multiple of this by some Gaussian integer, and it's an integer, that integer is divisible by p. Just like we did with the 5 thing. So let's try it. I minus a times b plus ci. Let's see what happens if that. Why is that divisible by p? Well, this is minus ab minus c. I guess that's yeah. Plus, let's see, we get minus ac plus bi. Okay? So this term is 0, so we find that b is equal to ac. And if we substitute that in here, we get minus a times b, which is ac, minus c. Right? Which is, factoring out the c, factoring out minus c times a squared plus 1. Correct? But a squared, because a was an I, a squared had the property of being minus 1 mod p. So a squared plus 1 is divisible by p. And consequently, if I have any product of I minus a with a Gaussian integer, which is an integer, that integer is divisible by p. So first thing we know is the intersection is pz, but on the other hand, I is congruent to an integer in but z to r mod I is surjective as I is congruent to an integer a in r mod I. Same argument that we used here. Once we have I congruent to an integer, any multiple of I is congruent to a multiple of that integer, so anything of the form b plus ci is congruent to an integer. So this map is surjective. Its kernel is precisely pz, so that identifies z mod pz with r mod I. And we've just proved that for any prime congruent to 1 mod 4, we have an ideal with this quotient. Now comes, that's already a great achievement, that Gauss had somehow the realization of all this structure that you needed to find. Okay, now here's the great idea. Next step. This ring has the property that every ideal in it is principal. This is Gauss's big theorem. We'll prove this later. Every I in R is principal. Notice that the ideal that we constructed here was not at all obviously principal. We needed this A, which was a fourth root of 1 mod p, and we needed r prime p. So we needed two generators for it. But abstractly, without considering the construction of this ideal, Gauss proved that every ideal is principal. So in particular, this one has to be principal. So corollary. Since every I is principal, so is this one. So we can write I is generated by some a plus bi. We don't know what a and b are, but there's some generator if it's principal. And consequently, R modulo the ideal generated by a plus bi is isomorphic to z mod pz, because that was true for r mod I. And then the last step is to show that this implies that a squared plus b squared has to be equal to p. I'll show you that next time. And that was Gauss's proof of Fermat's theorem that stated that any prime number congruent to 1 mod 4 was the sum of two squares. It was this A and this B that if you could write P as the sum of two squares, then every ideal in this ring had to be principal. It's an amazing observation. It's a ring theoretic proof. We don't know how Fermat proved this theorem. Fermat left nothing behind him in the way of proofs. He made statements. Most of his statements, a large number of his statements were correct. And they were so bizarre that he must have had something in mind. But Euler spent a great deal of his life trying to recover Fermat's proofs. And this is a great one that Gauss discovered using ring theory. So it really has two completely different steps. The first step is to show that for these primes there is an ideal with this quotient ring. The second step is to show that every ideal is principal. And then the third step, which is much easier, is to show that if you have a quotient by an ideal like this, more generally, I'll show you for the third step, the general statement to think about, and you guys can think about this for next time. More generally, the order of R mod the principal ideal generated by A plus BI is A squared plus B squared. The order of the finite ring, providing this is not the zero ideal. So here I would have a principal ideal such that the order of the quotient ring was P. That would force A squared plus B squared to be equal to P. It's a general statement. It has nothing to do with primes. That's just like saying the order of Z mod NZ is the absolute value of n. So here's some kind of absolute value. This is remember A plus BI times its conjugate. So this is like a complex absolute value. Think about that, and then you'll have the total proof of Fermat's theorem. And this is how ring theory was built. Gauss knew this result from Fermat, and he was trying to figure out how one would construct a mathematical proof of this that involves some structure. He was led naturally to this ring, Z plus Zi, because if you thought about A squared plus B squared, it was sort of like the absolute value of this element. Right? I mean, he knew complex analysis. Gauss also proved the fundamental theorem of algebra, which is a theorem in complex analysis. So he had worked with complex numbers. That led him to consider this subring of the complex numbers. And he realized that in proving this theorem, he had to prove something about its ideals. And that was the beginning of ring theory. So we'll go over the last couple of steps in this. Take a look through this. This is the work of a truly great mathematical mind. You're not supposed to come up with this overnight for your homework. But it's some appreciation of where the theory of ideals came about. And notice that you first construct an abstract ideal and then prove it principal theorem. Good. Okay, more on Wednesday.